Lesson 7 is about trigonometric integrals. So we're going to be integrating things where we have powers of different trig functions showing up. And there's different techniques that we're going to use depending on whether the exponents are even or odd and which trig function has the even and the odd exponent. Some things that we have used before, but we will use again to help us with these integrations are the Pythagorean identity that involves sine and cosine, the power reducing formula for sine squared, and the power reducing formula for cosine squared. So looking at first just number one, that number one there. When the power of sine is odd, like the 3 that's on sine here, and it's positive, but the technique that we are going to use is we are going to save 1 sine x for du, and we're going to change all the other signs to cosines. And you're going to change them to cosines using Pythagorean's identity. And once you have used the Pythagorean identity, you are then going to let u be cosine x. You're going to end up doing some substitution where your u is a cosine. Okay, so let's look at this example here. So I'm going to start off by saving 1 sine x factor. So instead of writing sine cubed x, I'm just going to write sine squared x, and then I'll have a cosine to the 4th x. And because I am saving one of those signs is going to show up right there. So I still do have sine cubed. I'm just writing it differently. I'm now going to convert the other signs to cosines. So I have a sine squared at the beginning of my integral. I'm going to change that sine squared to a 1 minus cosine squared x. And that's taking this equation and solving for sine squared by subtracting cosine squared from both sides of the equation. And then I'm just going to bring down that cosine to the 4th x and the sine x dx at the end. I'm going to distribute what's in the green to that cosine to the 4th. So we have the integral of cosine to the 4th x minus cosine to the 6th x, close parentheses. And I'll bring down this sine x dx. So we have changed the other cosine. You have changed the other sign to a cosine. So now we're ready to come in and let u be cosine x. So now that we have chosen u to be cosine x, we know that du, the derivative of cosine x, is a negative sine x dx. We don't have that negative on the inside of our integral, which is fine. So I'll just say that a negative du is positive sine x dx, which works out great because that's exactly what we have there. So inside our integral, we have u to the 4th, because we have cosine to the 4th, minus u to the 6th, because we have cosine to the 6th. And then everything else in purple is picked up by a negative du. So now when we integrate that, we're going to have a negative u to the 5th over 5 plus, so I'm distributing this negative. The first term will become negative. The second term will become positive. Increase your exponent up to 1, or increase your exponent by 1 and divide by your new exponent. And then I'll add my constant c. And then the last thing I'm going to do is just go back into this expression and substitute back in what u is. And that gives us negative cosine to the 5th x over 5 plus cosine to the 7th x over 7 plus c as our final answer. So keep in mind that these techniques are specific to the parity of the degrees. Parity just means whether it's even or odd, because if sine had not started off odd, then it would not have been even when we saved one, and then we would not have been able to even use a Pythagorean identity. Make sure you're paying attention to the parities, because the parities of the degrees are what's going to determine how you're going to go about that problem. Okay, so here in example 2, we have that the power of cosine is odd and positive, and so what we're going to do is we are going to save 1 cosine factor for du, and we're going to convert the other cosines to sines. So in this case, we're going to be letting our u be, we are going to well, we might not have to use a Pythagorean identity here, but we are going to be letting u be cosine x. No, sorry, sine x. U is going to be sine x. Okay. So example 2, I'm going to start off by saving one of those cosine factors that's in there. So I have the integral from pi over 6 to pi over 3. I'm just going to have a cosine squared on top now because I'm going to save one cosine at the back. So I've split up the cosine cubed into a cosine squared and a cosine. Now I'm going to come in and I'm going to convert any other cosines to sines, and I'm going to do that to this cosine squared that's up in the top because I'm going to use the Pythagorean identity that says that cosine squared is equal to 1 minus sine squared. So I'm going to go in and replace that numerator. So I replace the cosine squared in the numerator using a Pythagorean identity. Now I'm going to come in and go ahead and let u equal sine x. And then I'm going to go in and do the substitution. Well, let's pause for a second. I'll move this. If u is equal to sine x, let's go ahead and take our du. The derivative of sine is cosine, so our du is just cosine x dx. And so that's what's showing up right there. So now I'm ready to come in and do my substitution. Notice that I didn't put any limits on the integral. I'm going to go off to the side here and figure out what the limits need to be. We had old limits of pi over 6 and pi over 3. I'm going to change limits by plugging those x values into u, which is equal to sine x. When I plug in pi over 6, sine of pi over 6 is root 3 over 2. And when I plug in pi over 3, sine of pi over 6 is a half. And sine of pi over 3 is root 3 over 2. Okay, yeah, those were backwards. So the new lower limit is a half, and the new upper limit is root 3 over 2. I'm going to simplify the integral a little bit more because it can be broken up as 1 over the square root of u, and the square root of u we know is u to the 1/2. And then I'll also separate it into u squared over the square root of u, which is the same as u to 1/2. And then I'll take it a step further and I will rewrite this so that it will be in a form that is much easier for us to integrate. I'm going to subtract those exponents. 2 minus 1/2 is 3/2. Now I'm going to come in and integrate this. I'm going to increase my exponent by 1. Increasing negative 1/2 plus 1 gives us a positive half. Dividing by a half is the same as multiplying by 2. In the second one, I'm going to increase the exponent from 3/2 to 5/2, and I'm going to divide by 5/2, so I'm multiplying by 2/5, and I'm going to evaluate this from 1/2 to the square root of 3 over 2. So plugging in our upper limit of root 3 over 2, I have 2 times the square root of 3 over 2 to the 1/2 power, minus 2 times the square root of 3 over 2 to the 5/2 power. And then from all of that, we are subtracting, now I'm plugging in my lower limit, 2 times 1/2 to the 1/2 power. And then we add, because careful with your signs, I'd be subtracting a negative, a 2/5 multiplied by 1/2 to the 5/2 power, which comes out to be so this is an exact answer. Yeah, we could write that with a bunch of square roots as well. Either one is a perfectly good exact answer. You can check that in the calculator. You should be getting about 0.239. So when sine and cosine are both even and non-negative, or rather when the exponents are both even and non-negative, and the exponent on sine here is even because sine has an exponent of 0 on it, and 0 is an even number, and that is not negative. What we're going to do is make repeated use of the power reducing formula. So we're going to be using this formula here to integrate that. Then if we need to, we will be using number 2 if the power for one of our cosines turns odd. Okay, so I'm going to start off by realizing that cosine to the 4th is the same thing as cosine squared x squared. in the formula that we have right here for cosine squared x, I'm going to be replacing it with 1 plus cosine 2x over 2, and that's what we will be squaring instead. And then I will go ahead and actually square that. So when you square that, I'll just write it here. You're multiplying this by itself. You should, like, you're FOILing this out because, you know, we can split up that that fraction in the top. So when we FOIL that out, we should get a 1/4 plus cosine 2x over 2 plus cosine squared 2x over 4. And this all gets the dx on the end. So now I'm going to use the power reducing formula again because this right here, that cosine squared. So I'm going to keep the 1/4 that's at the front. I'm going to keep the cosine 2x over 2 that's in the middle. And then for what I circled, so I'm going to go grab a screenshot of that formula because we need to make sure that we are applying it properly. If we know that cosine squared x is equal to 1 plus cosine 2x over 2, be careful here because what we have over here, this is not an x, this is a 2x. So whatever was in here, what I circled in blue, is being doubled for what we're evaluating it as. So we're replacing x with 2x. So I would also need to replace this x with 2x. So this formula then becomes that cosine squared of not x, but 2x would be equal to 1 plus cosine of not 2 times x, but 2 times 2x over 2. So basically we're plugging 2x into this entire formula. So based off of what's over there, what I need to fill in here, because I've written everything else, I still have it even divided by 4, I just haven't filled in the numerator, is going to be 1 plus cosine 4x all divided by 2. Because 2 times 2x equals 4x. And then in that last fraction, we have, it's being divided by a 4. So I'm just going to multiply it by its reciprocal of 1/4 to really get that it's a 1/8 out in front of the 1 plus cosine 4x, because it's really 1 plus cosine 4x over 8. I'll just write it like that for now. Oh, that's over 8. Okay, so now we could break this up into really truly, we can break this up into 4 separate integrals. There's the integral of 1/4 dx. There's the integral of cosine 2x dx. Notice that this 2, there's a 1 over 2 there. I pulled that out there. This third one can be separated into 2 separate fractions, and then the 1/8 pulled out. So in other words, I'm saying I could pull this 1/8. You think of there's a 1 right here. This 1/8 out in front, and it would leave me with a 1 plus cosine 4x dx. And then I could separate this into 2 separate integrals. One with just a 1 on the inside, and one with just a cosine 4x on the inside. But you would have to make sure that you're bringing the 1/8 down with both of those. And some of you may not need to separate it down this far into all these individual integrals to be able to integrate it, but if you do, this is how it's done. So I'll start off integrating there's some like terms we could have combined, but it's okay. I'll start off integrating the 1/4 x to get an x over 4, or 1/4 x, plus, to do this integration in here, integral of cosine 2x dx, you're going to need to do a substitution. For u is 2x, du would be 2 dx, but we don't have a 2 in the integral, so we say 1/2 du is equal to dx. There's already a 1/2 out, Oh, there's an integral missing there, y'all. That integral is missing. Did y'all catch that? That integral right there. There's already a 1/2 out in front, so we would end up with a 1/4 the integral of cosine u du. And the integral of cosine is sine. So this would be a 1/4 sine u. So I'll sub back in what u is. U is 2x, so I have 1/4 sine 2x, or sine 2x over 4. Those are the same thing. Then I'm just going to be adding an x over 8, because the integral of 1 is just x. And then for that last integral, I'm going to get something similar. So watch this. There was already a 1/8 out in front, right? That 1/8 right there. This integral here with the 4x is going to be a lot like this integral in red with the 2x, except that u would be 4x. So instead of a 1/2 out front, we'd end up with a 1/4 out front. That needs to go with the 1/8 that was already there. And this will still be sine 4x plus c. So our final answer, these two can combine, make a common denominator of 8. So you have 2x over 8 plus x over 8 is 3x over 8 plus sine 2x over 4 plus 1 over 32 sine 4x plus c.